China now builds about 55% of the world's commercial ship tonnage, but the vessels behind this rise do far more than carry cargo. One 400-meter ship can hold 21,237 containers. A crane vessel can lift 12,000 tons. The Fujian carrier launches aircraft with electromagnetic catapults. Yet the biggest claim, a 125-megawatt floating nuclear plant, is not an operating ship at all. The real story is how proven machines, older breakthroughs, and unfinished plans reveal the reach of China's maritime industry. It begins inside the shipyards. The greatest Chinese ship is not one vessel. It is the system building all of them. Along China's coast, giant dry docks sit beside forests of cranes. Inside them, workers assemble container ships, research vessels, drilling platforms, and warships. These machines serve different purposes, but they grow from the same wider industrial base: steel mills, engine makers, electronics suppliers, trained workers, and some of the largest shipyards on Earth. UN Trade and Development reported that Chinese yards produced about 55% of global shipbuilding output by gross tonnage in 2024. That number is easy to misunderstand. It does not mean China owns 55% of every ship already sailing. It means more than half of the new commercial ship volume completed that year came from Chinese yards. Scale helps explain how this happened. A large flow of commercial orders keeps docks busy and workers experienced. Suppliers can produce parts in huge numbers. Skills learned while building a cargo ship may also help engineers solve problems involving stronger hulls, larger power systems, or complex deck equipment. State support has helped the industry expand, while China's steel sector and export economy create steady demand. Yet the system is not one secret naval factory. Some yards focus on civilian work. Others build both commercial and military vessels. Their ownership, customers, and roles are not all the same. There is another important correction. Many Chinese vessels described online as new are not new at all. Some entered service between 2012 and 2019. They matter because each one helped develop knowledge that could be used in later projects. The real advantage is not simply size. It is repetition. China can design, build, test, and improve many kinds of large vessels without rebuilding the entire supply chain each time. Stay with this story, because its largest and most futuristic claim leads to a very different truth. First, the scale of this system can be seen in the cargo giants built inside it. A single container may not look impressive. Place more than 21,000 of them on one ship, and the scale becomes difficult to picture. COSCO Shipping Universe shows what China's shipbuilding system can produce when cargo capacity becomes the main goal. Delivered in 2018, the vessel is almost 400 meters long and 58.6 meters wide. That makes it nearly as long as 4 football fields placed end to end. Its stated capacity is 21,237 TEU. TEU means 20-foot equivalent unit. It is the shipping industry's standard way of counting containers. 1 TEU represents one normal 20-foot box. The universe can therefore carry the equivalent of more than 21,000 of them, although its real load changes with container size, weight, and safety limits. The ship is not alone. COSCO Shipping Galaxy belongs to the same 6-vessel Universe class. These are sister ships built from the same basic design, not separate inventions. Universe set a Chinese record when delivered, but larger container ships have since entered service elsewhere. Calling it the world's largest today would be wrong. China also built 400,000 deadweight ton or carriers, including Tianjin and Yuan-He-Hai. Deadweight does not describe the empty ship's weight. It measures how much cargo, fuel, supplies, and other load the vessel can safely carry. These giants were created mainly to move iron ore over long routes, including the journey from Brazil to China. The advantage is simple. One large ship can move more cargo in a single voyage, lowering the transport cost for each container or ton of ore. Yet size creates its own problems. These vessels need deep water, huge cranes, strong docks, and enough cargo to keep them full. They cannot enter every port. A delay in a major canal or terminal can hold up an enormous amount of trade at once. That is why these cargo giants matter. They are not just floating records. They connect Chinese factories with distant markets while proving that the country can build at extreme scale. Carrying goods across the ocean is one challenge. Reaching energy buried thousands of meters beneath it requires a completely different kind of machine. It floats like a ship, stands like a building, and can drill deeper than Mount Everest is tall. Haiyang Shiyu 981, often shortened to HYSY 981, is not a normal vessel. It is a semi-submersible drilling platform built to search for oil and gas far offshore. It began operating in 2012 and was designed to work in water as deep as 3,000 meters, with a maximum stated drilling depth of 12,000 meters. Those numbers describe two different distances. Water depth measures the space from the ocean surface to the seabed. Drilling depth measures how far the well can continue through the rock below it. A semi-submersible platform stays stable by placing much of its supporting structure beneath the roughest surface waves. Large columns connect the working deck to underwater pontoons. Ballast tanks fill with seawater to lower the structure into its working position. Powerful thrusters and positioning systems then help keep it over the drilling point. Think of it like a person standing with their legs deep in a swimming pool. The moving surface still pushes against them, but the strongest support remains lower and steadier. China later introduced Haiyang Shiyu 982. Published reports describe it as another sixth-generation semi-submersible platform, designed to drill more than 9,000 meters and survive winds near 200 kilometers per hour. These are design limits, not proof that every well reaches that depth or every mission faces such weather. The engineering also carries political weight. In 2014, China placed HYSY 981 near the disputed Paracel Islands. Vietnam said the platform was operating inside its waters. China rejected that claim. Ships from both sides gathered around the rig, creating a tense standoff that lasted for weeks. The platform had become more than an energy machine. It showed how industrial ability could strengthen a country's position in contested seas. Is this mainly an engineering achievement or a strategic tool? Share your answer in the comments. Drilling beneath the seabed extends China's reach downward. Its next group of vessels moves in another direction, toward polar ice and the deepest parts of the ocean. In thick polar ice, moving backward can be just as important as moving forward. Shuelong 2 was completed in 2019 as China's first domestically built polar research icebreaker. The ship is 122.5 meters long and uses two steerable electric propulsion units. These can turn and push water in different directions, giving the vessel greater control in difficult ice. Its hull can break ice while traveling forward or backward. At about 3 knots, the ship can move continuously through ice roughly 1.5 meters thick. That sounds slow, but forcing a 14,000-ton vessel through solid ice is not a race. The goal is steady movement without trapping or damaging the ship. Shuelong 2 carries scientists and research equipment into Arctic and Antarctic waters. It supports studies of the atmosphere, oceans, geology, and living systems. It can also deliver supplies to remote research stations. This gives China access to regions where climate change, shipping routes, and natural resources are becoming more important. Another vessel, the Yang Hao, looks toward the seabed instead of the ice. Placed into service in December 2019, it was designed for ocean science and mineral resource surveys. Sonar maps the ocean floor. Samplers collect rocks and sediment, while underwater machines examine places far beyond the reach of divers. These surveys may locate polymetallic nodules. They are rock-like lumps containing metals such as nickel, cobalt, copper, and manganese. These materials can support batteries and modern industry. Yet finding them is not the same as mining them. Large-scale commercial seabed mining has not become a normal global business, and serious questions remain about cost and environmental damage. Research voyages can also produce information with strategic value. However, unusual routes or seabed mapping do not prove that a vessel is conducting military surveillance. The confirmed evidence supports scientific and resource missions. Anything beyond that requires stronger proof. These ships help China observe places most people will never see. But studying the ocean is different from physically rebuilding it. For that task, China created a vessel able to lift entire structures from the sea. One ship can lift a structure that weighs more than the Eiffel Tower. Zhenhua 30 is a self-propelled crane vessel built for jobs ordinary equipment cannot handle. It is almost 298 meters long and 58 meters wide. Above its deck stands a single boom crane with a stated maximum lifting capacity of 12,000 tons. Lifting that weight on land is difficult. Doing it at sea is harder because the vessel, water, crane, and load can move at the same time. A swinging load can place enormous stress on the cables and boom. The ship controls this risk through size, balance, and planning. Its wide hull creates a stable base. Ballast water can move between tanks to balance the changing load, much like shifting weight across a scale. Anchors and positioning systems help hold the vessel in place. Engineers also study the wind, waves, lifting angle, and center of gravity before movement begins. The 12,000-ton figure is a maximum rating, not a promise for every situation. Safe capacity changes with the boom's position, the load's distance from the vessel, and conditions at sea. Some operations must wait for calm weather. Zhenhua 30 helped install major sections of the Hong Kong-Zhuhai-Macau Bridge. In 2025, its operator reported that it lifted a 10,000-ton offshore steel structure near Guangdong. Work that might require long assembly at sea can instead be completed by lifting one huge section into position. That ability supports bridges, oil platforms, offshore wind farms, and other coastal projects. The vessel is impressive, but the larger achievement is control, moving thousands of tons and placing them where engineers need them. Subscribe for more clear breakdowns of the machines quietly reshaping the modern world. China had shown that it could lift giant structures above the sea. Its next leap involved launching something much faster from a moving deck, advanced military aircraft. The most important aircraft on China's newest carrier may not be the one designed to attack. It may be the one built to see farther. Fujian is China's third aircraft carrier and the first Chinese carrier equipped with electromagnetic catapults. It was formally commissioned on November 5, 2025, after a series of sea trials. With a full load displacement reported at more than 80,000 tons, it is China's largest warship. The change is easiest to understand by looking at China's first two carriers. Liaoning and Shandong use curved ski jump ramps. A fighter races up the ramp and uses its own engine power to take off. That works, but the aircraft's weight, fuel, and weapon load can be limited. Fujian has a flat deck. Its catapult pulls an aircraft forward along a track and helps it reach flying speed. Think of it like giving the plane a powerful push before it leaves the deck. Because the force can be controlled, the system can launch different types of aircraft at different weights. Official Chinese reports say the J-15T fighter, J J-35 stealth fighter, J-15DT electronic warfare aircraft, and KJ-600 early warning plane have completed catapult launches and arrested landings on Fujian. An arrested landing means a hook beneath the aircraft catches a strong cable across the deck, stopping the plane in a very short distance. The KJ-600 may provide the greatest change. Its large radar can watch a much wider area than sensors mounted on the ship. It can help detect aircraft or other threats earlier and share that information with the carrier group. Yet commissioning is not the same as full combat readiness. Fujian is conventionally powered, so it lacks the long endurance of a nuclear-powered American carrier. China must also train pilots, manage crowded deck operations, maintain the catapults, coordinate escort ships, and learn from long deployments. The United States still has far more experience operating carrier groups around the world. Fujian gives China a stronger tool, but it does not guarantee control of any sea or decide the result of a conflict. Its real test will be how safely and reliably the entire group operates over time. Launching aircraft demands enormous energy. That leads to the most futuristic claim in this story, a Chinese vessel said to carry a 125-megawatt nuclear power station anywhere on Earth. The most futuristic vessel in this story is also the one missing from the water. For years, reports and concept images have described a Chinese floating nuclear plant that could power remote islands, offshore platforms, or coastal areas. The idea centers on ACP-100S, a floating version of China's small pressurized water reactor technology. Published designs describe output as high as 125 megawatts. A reactor uses heat from controlled nuclear fission to make steam. The steam turns a turbine, producing electricity. Placing this system on a floating platform could deliver steady power where building a land station is difficult. That is the concept. It is not a working ship. China discussed demonstration floating plants years ago. However, plans linked to the South China Sea were reported suspended in 2023 over safety and feasibility concerns. A floating reactor would face storms, corrosion, collisions, security threats, and the challenge of handling an accident far from emergency support. Confusion grows because China is building a real reactor called Linglong-1, or ACP-100. It has a gross electrical capacity of 125 megawatts. Yet Linglong-1 stands at the Changjiang nuclear site in Hainan. It is not on a vessel. The International Atomic Energy Agency still listed Linglong-1 as under construction on July 22, 2026. Its public record showed no first criticality, grid connection, or commercial operation date. There was also no reliable public evidence that China operated an ACP-100S floating station at sea. China could return to the idea, and the design work still matters. What remains unproven is whether it can build, license, protect, and safely operate such a station offshore. This correction reveals the larger story. China's real maritime power comes from an industrial system able to build cargo giants, drilling platforms, polar research ships, deep-sea survey vessels, construction machines, and advanced aircraft carriers. No single ship will change everything. Together, these machines can influence prices, resources, construction, science, and military planning. Their impact will still depend on safety, demand, trained crews, environmental limits, and international response. Like and share this story with someone who should know the difference between a working machine and a future concept. The ocean's future will not be decided by the biggest claim. It will be decided by the systems that can keep building, operating, and improving after the headlines disappear.